So good afternoon, everybody. It's my pleasure today to introduce to you Xuan Zhang from Aerodyne Research Incorporated. Xuan is visiting with us today. She got her bachelor's degree at Beijing Normal University and stayed in the region at Peking University to do her master's work, doing some very unique aqueous phase oxidation chemistry. She then crossed the ocean and ended up at Caltech working with John Seinfeld's group for her PhD work, largely working on the chamber systems there and looking at oxidative chemistry of monoterpenes. She's doing a little bit more instrumental type of work these days at Aerodyne, where I think she's been for about a year now. So with that, I'll introduce Xuan, and her title of her talk is Understanding the Signature and Chemistry of Atmospheric Organic Aerosols.
Thank you. Thank you, guys. And it's a great pleasure for me to be here and sharing my thoughts and experiences on atmospheric chemistry research. I'm going to talk about particles in the air, how they are formed, and what they're composed of. Before I get started, I would like to acknowledge my PhD advisor, John Seinfeld, Rick Flagan, and the Caltech Environmental Chamber Group. This photo was taken in 2012 when we first built our new chamber without handing the bag yet. And Christine and I are handing the bag. And I would also like to thank my current coworkers, Doug, John, and Manjula, and also my collaborators, Chris Kappa from UC Davis and Jason Surratt from UNC for their great support and help. I would like to start with this well-known figure. I'm sure you have seen it for quite a few times, so I will get briefly. This figure just shows the chemical composition of particles in all over the northern atmosphere. And the message here is organic content is widespread, account for half the aerosol mass. They're important and they're everywhere, and they're highly oxygenated. Our science community has realized the importance of organic aerosols in climate or health impact for quite a while. But our understanding for their sources, chemistry, or lifetime is still rather limited. So this figure shows 17 aircraft campaign data was used to constrain the performance of the standard geochem. And this figure shows that out of 13 campaigns, the geochem underpredicts the aerosol loading by a factor of 2 to 10. Especially the large bios is from the anthropogenic reason. Well, this underestimation clearly demonstrates our incomplete understanding on the organic aerosol mass in the air. While there have been few research programs developed, such as cloud processing and unknown precursors, or missing low volatility compounds in product, or the potentially underestimated SOA yield. And throughout my PhD, one focus of my research is to try to understand if the underestimation of the SOA yield. Well, because most 3D models parameterization of organic aerosol relies on the chamber observations. Well, let's first look at a typical chamber experiment, the key processes in such an experiment. So when a volatile organic compound, here is isoprene here, is exposed to key oxidants such as OH radical, it will undergo multiple generations of oxidation, producing highly functionalized and low volatility products. Because they have low volatility, they can nucleate to form new particles, or they can condensing onto existing particles, producing secondary organic aerosol. And in the particle phase, heterogeneous chemistry can still going on and changing the chemical signature and probably the phase state of the particles. And of course, they are sticky vapors. They're expected to be deposited onto the wall. There are 3 phases for the particles formed. they can continue interaction with the gas phase vapors, and they can grow bigger by coagulation, or they can lost on the wall. I would like to draw your attention to these two processes. So you see that if organic vapors are lost onto the wall, then there will be less vapors available for the particles. Thus, our derived SOE yield will be underestimated. And the yield here is defined as the mass of particles formed over the mass of hydrocarbon reacted. And if this yield is underestimated, then this is one of the possible reasons that global model cannot predict the OA budget now. So our question is, how can we interact the vapor wall interactions, and how can we understand the impact of such interactions on the derived SOA yield? So we first build a theoretical framework. Here the blue line shows a concentration profile of organic vapor I in the well-mixed core of the chamber, in the boundary layer, and in the wall. When I say wall, it means the Teflon sheets, the bag. So the red arrows means represents the vapor fluxes over the wall surface. So the general physical picture here is that organic molecules, they can be transported to the wall through either molecular diffusion or turbulent mixing. And there is a thin boundary layer near the wall where the steady state can be reached, so that at any point in this boundary layer, the concentration of the vapor I is a function of its concentration in the well-mixed core. And when the organic vapor molecules met the wall, not everyone could stuck onto the wall, and some will bounce back to the gas phase. And so we define a parameter called wall accommodation coefficient to describe the fraction of molecules that can be stuck onto the wall. And over the wall surface, there are vapor fluxes into the wall due to condensation and outside the wall due to evaporation. And at a liquid equilibrium state, and these two processes should be equal to each other. So we built this framework, and we also did some experiments to verify or constrain our framework. So this figure shows how the organic vapor are generated and decreased due to the wall-induced deposition. And by constraining our theoretical framework, we can eventually predict the vapor wall loss rate of any compound based on their molecular information, which is here oxygen number and carbon number. So this figure shows you that within a certain volatility range, the vapor wall loss rate is increasing along with decreasing volatilities, eventually reaching the highest value here, which is ultimately controlled by the chamber mixing state. And you might notice that the maximum occurs right here instead of the right corners. Well, this is because when wall accommodation becomes fast enough, the limiting step is no longer the wall accommodation. It becomes the gas phase transport. For the molecules right here, their gas phase transport is too slow, thus limiting their wall deposition rate. And the figure on your right hand shows that under what circumstances the wall impact really matters. So here, the color map shows the time scale for the gas particle partitioning as a function of the seed surface area and a function of the gas particle accommodation coefficient. And the white line right here shows you the estimated time scale for gas vapor wall loss as a function of the gas wall accommodation coefficient. You see that when these two time scales are close to each other or they overlap, this means the vapor particle partitioning and vapor wall partitioning are competing with each other. Under these circumstances, if vapors are lost onto the wall, then they're not available for the particles, and then they will impact the SOA yield. So we want to really know how much the SOA yield is impacted by this vapor wall loss procedure. So we run on a series of experiments investigating the photooxidation of toluene under both high NOx conditions and low NOx conditions to try to simulate extreme urban and rural conditions. And we maintain all the conditions consistent, but just vary the initial ammonium sulfate seed area. And what we see is the aerosol mass yield is increasing along with increasing seed surface area. Well, this is sort of expected. You can simply think that the gas phase molecule can transport when they are transporting all the way to the wall, and they meet more particles and they stuck with them. So you would get a higher yield when you have higher seed surface area. Well, is this really a perfect demonstration of the wall impact? And it turns out it's more complicated than we thought. So this is a simulation results showing that the SOA yield dependence as the initial seed surface area when we consider the wall impact. And we see the trend, which is consistent with our experimental results. But for the top three line, there is no wall impact. We still see the trend. Why was that? Well, it turns out for a chamber system, we can't just simply consider gas wall and gas particle. We have to also consider the gas phase oxidation. You can think of this problem this way. If we let the gas particle partitioning to be really, really slow, then more gas will just oxidize or react in the gas phase. They won't go to the particles. So there is also a competing process like right there. So this figure essentially shows you that as historically, most 3D models would parameterize yield as a function of organic mass loading. And turns out, if the particle growth is kinetically limited, you can't just simply do such a parameterization, because the dependence comes from not only the wall impact, but also the kinetic growth. And so finally, we want to know, what is the SOA yield under wall-free conditions? Well, we can't build a chamber large enough, so we have to run simulations. And we define a parameter called R-wall. We call wall bias, which is defined as the SOA yield under wall-free condition divided by the measured SOA yield we did in the chamber. And what we found is if we increase the toluene and OH concentration to be extremely high, the bias eventually will approach 1. This means no wall impact. So basically, this simulation demonstrates that for the purpose of minimizing wall loss, we need to start with a very high concentration to get the reaction speed up. And finally, this figure shows a regional model prediction on the organic aerosol versus the CO ratio in Riverside, California, 2005. Here, the SOM no, low, and high represent in the absence of wall, considering the wall impact, and the low limit of the wall impact and the high limit of wall impact. And you can see that the high end, by considering the wall impact, really captures the diurnal trend and the concentration. So potentially accounting for the vapor wall loss, you could close the gap between the model predictions and the field measurements. So I will give a short summary right here. So we built a framework to try to describe the vapor wall interactions in a chamber. And we run experiments to verify our framework. At the same time, we also investigate the impact of wall loss on the SOA yield, a parameter that has been used in 3D models to represent the organic aerosol budget in the air. Well, through this project, I have been realizing that SOA yield is only essentially a mathematical representation of the SOA forming potential of any given precursor. Well, it is in fact the individual molecules who really play a role during the SOA growth. So this shifted my attention to try to explore the behavior of individual molecules during SOA growth. So I start to think, what would be the adequate instruments to get a time-resolved molecular profile of organic aerosols? As we know, traditional filter sampling, they suffer from time resolution. And most online instruments for the particle phase, they use hard ionization scheme, and they break everything apart, and you essentially get all the fragments. So what I want to do is something soft, and you still get the profile, and you still get the molecular intact structure. So I came up with the idea of combining the particle into liquid sampler with a liquid chromatography together with the mass spectrometry. The pills was first introduced by Rodney Weber in 2000. It has been widely used since then for collecting inorganic ions such as sulfate and organic water-soluble organic carbon. So the working principle here is the aerosol flow passing through two denuders to remove all the gases. And a water steam generated at 100 C, it will mix with the cooler aerosol flow adiabatically and thus creating a supersaturation environment to eventually grow particles big enough to be collected by inertia impaction on this quartz impactor. And the collected particles are then delivered into a debubbler to remove all the gases and then infused to the vials held on a rotating carousel. And the collected liquid sample was then infused to a LC column where compounds with different polarities can be separated. The separate compounds were further ionized by the electrospray, which is a soft ionization technique that can maintain the intact structure of molecules, and the ionized molecules were further analyzed in a top chamber and got detected. So it seems like a good plan, but you might realize that the big issue out of this method is pills is used to collect particles by water. That means it's reasonable to think that it might not apply to all the aerosol types, because what if the water insoluble component, how are you going to collect them? So the first problem we have to deal with is the collection efficiency of this system. So we first run a simulation on the hygroscopic growth of particles in the Pill's condensation chamber. And this figure shows that for a particle size distribution from 20 to 800 nanometer, as long as the water optic coefficient is higher than 10 to the minus 2, and the particles can be grow higher than 1 micrometer within 1 second. What does this mean? So the 1 micrometer means the threshold for particles can be collected by our impactor. And the 1 second means the resin time of the growth chamber. And 10 to the minus 2 means that out of 100 times the water and particle collisions, only 1 water molecule was stuck onto the particles, which means that the particles is pretty not hydrophilic. So we further run some calibration experiments to try to verify our model output. So we compared the pulse collected organic mass with the DMA measured mass for a variety of, a collection of species with varying water solubility and volatility. So here we classify the water solubility as inorganic I, slightly soluble, and soluble. And the volatility is ranged from intermediate VOC, semi, and low volatility. So what we see here is there is definitely a very clear trend of the collection efficiency on the water solubility. But the more important information is even for a slightly soluble compound, the pills can still work pretty reasonably well. So both our experimental results and simulations have demonstrated that pills can work for slightly water-soluble species. The reason underneath this is that you generate water vapor at 100 C. So there is a huge imbalance in the water pressure far away from the particle and over the particle surface. This huge pressure imbalance could overcome the mass transfer resistance over the particle surface. So even the particles are not that water soluble, you can still somehow grow them by water. Well, similar principle with the condensational particle counter. I'm going to skip all the other details in the method development, but just show you some application results. We use this technique to study the SOA formation and evolution from the ozone lysis of alpha-pinene. This shows a product distribution at the moment when 90% of alpha-pinene is reacted with ozone. And the x-axis is the carbon number, and the y-axis the carbon oxidation state. The color bar represents the volatility of the product, and the size represents the mass concentration of the particle molecular component. So what you can see out of figure is Oh, the gray dashed line is the AMS measured average oxidation state of the particle mass as a whole. And you can see it's actually consistent with what we observed for individual molecular components. So what you see out of the picture is that the products are composed of monomers and dimers. And for the monomer region, they're characterized as carboxylic acid group. And the volatility ranges from SVOC to LVOC. And for the dimers, they're mostly characterized by this ester group and, of course, acid group. And with the volatility ranging from LVOC to ELVOC. Now, if we plot the time profile of every individual product, what we can see. So here's the figure showing their growth profile. And it's a kind of messy, so let's group them into 3 categories: semi-volatile SVOC, low-volatile LVOC, and extremely low-volatile. And by looking at their growth profiles, we can actually further examine their dynamics. So here you can see that over the course of 4 hours of experiment, the SVOC is really the dominant component. And the ELVOC and LVOC only accounts for less than 40% of the total organic carbon mass. But if you pay attention to here, the prompt formation of ELVOC really initiates the particle growth. But as the reaction goes on, its production was inhibited. So the prompt formation ELVOC also indicates that there's no kinetic barrier for its production, and further indicates that they are not produced from the condensed phase accretion reactions as we thought traditionally. So this figure just shows the mass fraction of each molecular component under different temperature and different relative humidities. And this figure will tell you some information on the dominant processes governing the SOA production. Or let's just look at the temperature effect. So if you decrease the temperature, you would decrease the volatility of product. And you would imagine that you will induce more condensing onto the particles. Well, this is true for the monomers, but not true for the dimers. So we actually propose that a solvation process might play a role in this part of the dimers. And if you want to know more details about this, and you can refer to our paper published last year. So a short summary for this method development. We combined pulse with UPLC mass for a time-resolved molecular characterization of organic aerosol. And we applied this technique to study the organic aerosol formation from ozone lysis alpha pinene. And we can actually resolve 60 to 70% of the total organic mass. Well, then we are wondering, what is the missing 30% carbon mass, what they are and where they are? As you might know that many recent studies, they have used gas phase sieves to measure all these highly oxidized molecules. And the distinct feature out of these molecules is that they contain oxygen numbers more than 6 with a C8 to 10 carbon backbone. And due to the low volatility of these products, they actually constitute a widespread source of organic aerosols over the regions with minimal human impact. Well, this potentially explained that the fogginess environment over the forest, and also shed lights onto the cloudiness in the pre-industrial air. And it has been proposed that these molecules are produced from the auto-oxidation chemistry, where you have crazy H shift followed by O oxygen addition, and eventually give you these highly oxidized peroxide. Well, peroxide has been measured in many gas phase instruments, but they have not been measured in the particle phase. Why was that? Well, because they are labile and thermally unstable. They can totally decompose, and we can't track them. Well, let's keep this in mind because I will come back shortly. So I will spend the rest of the time talking a little bit about my work at Aerodyne, where I was lucky to work on a new type of technique called Ion Mobility Mass Spectrometer. The working principle of this technique is that the ions are traveling through a drift tube under a weak applied electric field. During their travel, they can encounter and collide with neutral molecules, which is nitrogen here. And as a result, a steady flow of ions can be developed along the field line, and as a result of the deceleration due to the collision with the nitrogen molecules. Well, you can imagine that different ions, they will have their different structures, compact, extended. And thus, they will have a unique collision cross-section with the nitrogens, which determines their time spending in this drift tube. You can think of that the ions with more like extended structure, they will stay in the drift tube longer than those compact ones. So you will end up getting a chromatograph like a figure showing the molecules with their different drift time. So what if you combine the drift tube with a time of flight chamber? So you will get a two-dimensional separation rather than a simple mass spectrometry. So this type of figure is what you can get out of this technique. So any point on this space, you can get information on their mass and size, which is reflected as mass charge ratio, and also the geometry. So what we're really interested is how to apply this technique to resolve the complexity of the organic aerosols in the air. So the framework we are developing is based on this technique, which shows that the x-axis is the mass to charge ratio and the y-axis is the collision cross-section with nitrogen. Let's first look at how the compounds are distributed on this mass. So here, this figure shows the distribution of amine, ester, alcohol, and carbonyl on the positive ESI mode. And this figure shows the distribution of all different sorts of acids and sulfate on the negative ESI mode. There are two distinct features out of this distribution. First, you can see that the species with higher density, they tend to sit at the lower panel of this space. This is not surprising because if a species have lower collision cross-section, they tend to be much denser or potentially highly functionalized than those with open and extended geometry. The second feature is that you can see that species coming from the same functional chemical class, and they tend to occupy in a narrow region and follow a distinct trend line. I would like to call your attention on these trend lines because they form the basis for the identification of chemical classes that unknown compound will belong. Well, actually, we can predict the trend lines by understanding the fundamental basis involved in the ion molecule interactions. I'm going to skip the details on this model, but just show you some results. So this three figure shows the application of the predicted trend line to three important classes: amines, alcohols, and carboxylic acids. So the colored marker represent our measured collision cross-section for a selection of chemical standard we bought. And the solid line represent our model prediction on the trend line. And the shaded area you see is the measurement and model measurement and prediction disagreement, which is within 8% uncertainties. Well, let me just briefly show you where is the uncertainties come from. It comes from the simplification of the ion structures in our model. You see here, the benzoic acid is deviating from the line for the alkanoic acid due to the presence of the aromatic ring. But the take-home message here is that we can use the trend line and the location to at least know that what functionalities an unknown compound might contain, which would greatly facilitate our further structure identification of the unknown molecules. Well then, what if the trend lines are overlapping each other? Now we need to add another dimension of separation, which is collision-induced dissociation, we call CID for short. Let me briefly introduce how this works. So the drift tube was operated at ambient pressure, while the time-of-flight chamber was operated under vacuum. So there is a huge pressure drop in this interface. And if you apply voltage on this interface, you will have more collisions that eventually break the ions apart. And because the drift tube is operating ahead of this, so you would imagine that the parent molecule and the daughter molecule, they actually have the same drift time. This would greatly facilitate that you can correlate the fragment molecule with the parent molecules, right? So this figure shows the characteristic fragments for 6 species that are representative of aldehyde, nitroorganic compound, amine, acids, and esters. For example, a neutral combined loss of CO2 and water is expected if it's a diacid. If there is a OH group next to the carboxylic acid, then you would expect a loss of formic acid. So the message here is that if you know the fragmentation pattern and you know the typical fragments, this would greatly facilitate you to identify the unknown compound structure. So now you might notice that so far the molecular constituent I have covered include amines, alcohols, carboxylic acid, esters, and to name a few, but I never mentioned the organic nitrate and peroxides. Well, it doesn't mean they're not important. In fact, they're really important in a way that they're representative of 2 distinct chemical reaction categories, both in the remote environment and the polluted environment. Well, there have been many adequate instrumentation to try to characterize or measure their levels in the gas phase, but their characterization in the particle phase remain limited. This is mainly because they are very fragile and they decompose very easily. So I'm going to use the following few slides to show you our recent effort to measure those compounds in the condensed phase. We're still using ESI as my favorite. This figure shows you how the working principle of the electrospray. So you have the analyte solution infused to a capillary under a high voltage applied. And as a result, because this is a negative potential, and all the negative ions, they tend to escape from the solution. Eventually, you have a Taylor cone produced. And when the force due to charge repulsion is higher than the force constrained by the surface tension, the Taylor cone will explode and releasing all these negative ions. The key question to ask here is, what are these ions are composed of? Well, first, they can be the anions naturally in the solution, like sulfate, nitrate. Or they can also be produced from the deprotonation of polar species, like carboxylic acid, which would be a good candidate for this kind of negative ESI. And it turns out for the molecules which don't have labile hydrogen, they can combine with the existing anions in the solution on forming the clusters. And this figure shows you that for the 3 selected nitrate, or you call explosives, they don't have a distinct molecular ion spectra on their own. But if you add selected anions into the solution, including chloride, acetate, nitrate, and iodide, they can form high intensity of the molecule clusters. So you can consider this ion scheme as the chemical ionization in the condensed phase, which is a really neat method to detect those explosive, unstable nitrogen molecules in the condensed phase. In this figure, just again show you the characteristic fragments to further facilitate the identification of their structures. And we actually found that the ion clustering scheme also works for the organic proxies by using some standards. And now I'm going to come back to this missing carbon in the alpha-penning SOA. And we think using this ion clustering scheme in the positive ESI, by clustering with the sodium cation, we sort of able to track the highly oxidized gas phase molecules in the condensed phase. But I mean, this figure alone cannot 100% demonstrate these are those proxies. But we have some further ongoing experiments, including using different deuterated alpha-pinene to try to figure them out. Okay, so a summary on this part is that we are trying to find a way for the application of the Ion Mobility Mass Spectrometer, and so far we focus on two aspects. First is to build a two-dimensional space to try to deconvolve the complexity of organic aerosols. And the second is more like a highlight of working on towards these highly unstable compounds in the condensed phase, organic nitrates and peroxides. So I would like to use this figure to give you a summarize of my research effort and hopefully touch a little bit on the future directions I would like to pursue. What I have been really interested in is the oxidative chemistry in the atmosphere and how this chemistry leads to the formation of organic aerosols. And throughout my PhD, I have used the chamber facility to try to understand the atmosphere processing of the biogenic emissions and the anthropogenic emissions. Then my current research effort is to try to characterize the organic aerosols with different flavors of mass spectrometry and then infer their formation pathways depending on this information. So if you ask me, why do I study aerosol? I would tell you that, okay, they have impact on global climate and human health. Well, my research has been really focused on the early stage of this picture. But I have also been thinking about how to link the atmospheric chemistry to the physical weather system and to the biosphere. Particularly, I want to ask myself how to parameterize the organic aerosol adequately and efficiently when assessing their impact on human health and global climate. So the studies in the past 10 years have strengthened the causal association between PM2.5 exposure and the adverse health outcome, primarily including the cardiovascular diseases and the respiratory diseases. So this figure shows you a typical approach employed in epidemiological studies. So here you first assign exposure as accurate as possible. And most studies have been using the fixed location monitors or the national monitoring network to assign exposure. And then you establish a disease model. And then you estimate the health impact by a multi-component analysis. Well, in my opinion, an issue coming out of this method is the inaccurate exposure assignment. So particularly, there are two issues. First, the ambient monitors, their measurements data are sparse over the space, and they usually don't have daily basis data. And second is that all the components from the same source, they're highly correlated with each other. And it's really a challenging task to try to separate their health impact of one single component from all the other components. And when it comes to making a list of actions to try to minimize the health impact of PM as a whole, and we must, important to know that which component is the most harmful to our human being. And I think I noticed that a few recent studies, they have actually used regional models to try to assign the exposure, which in my opinion is a very practical and efficient way for future epidemiological studies. Well, speaking of the model representation, now let's look at, in my opinion, how aerosol is parameterized in models. I know there are a lot of experts as audience, so please feel free to correct me. So the traditional approach to represent SOA formation is embodied in the two-product model, where you have two products along with the mass yield and partitioning coefficient to represent the SOA as a whole. And these parameters need to be constrained from the chamber data. And the volatility basis set is a sort of extension of the two-product idea, where you assign product to different volatility bins. And in this case, during multi-generation oxidation, you can assign each generation product different bins to try to represent the SOA evolution. And during this case, the stoichiometric coefficient during this assignment is, again, from the chamber data constraint. And I noticed that recent efforts have really tried to incorporating elemental information to the 3D models. And I will use the statistical oxidation model as an example. So basically, it uses a space of oxygen and carbon atoms to try to represent organic aerosol. So you can think of each point on the space, they can be a virtual product with assigned carbon and oxygen numbers. And so this space can represent the key processes in the SOA formation. So you can think the functionalization would be the addition of the oxygen. And the fragmentation can be the removal of the carbon numbers. And again, the stoichiometric for each bin comes from the chamber data constraints. So you can see that there's a trend to consider more and more chemical information into the 3D models. I mean, frankly, to mapping out every single product in the model is not going to be practical and would consume too much computational effort. But I think more molecular information incorporated, such as functionalities or chemical classes, might be achievable in the future. And if that's true, it will at least greatly benefit the epidemiological studies. So I would like to end my talk with this cartoon and hopefully bring up some discussions on the atmospheric chemistry in the changing climate and the role of aerosols in the climate. So with this, thank you for your attention.
So questions for Xuan, and we'll try as best as we can to use the microphone because we are being recorded.
Hi, thanks. That was really interesting. I had a question just about the first part of your chamber and the wall loss studies. So are people applying your new model to predict the wall losses to recalculate all the yields that are being used in all the models? Are we going back and re-evaluating the way that we're modeling SOA formation using the two-product model?
Yes, I think the SOA yield from toluene has been incorporated in certain regional models to try to improve the prediction capabilities.
Have you seen those results? I mean, is it making the models do a better job at predicting SOA?
Clearly, yes. Because I think the most model and measurement disagreement comes from the anthropogenic region. And the most dominant precursors in the anthropogenic region is aromatics and launching alkanes and alkenes. And so.
Other questions? Wow. Britt. I think you put your hand up.
Yeah.
You did now.
I was just curious how, what does the drift tube instrument look like? Is it something you could deploy in the field, or is this really only suitable for laboratory studies?
Well, for now, it's an offline instrument. So basically, you need to collect their filters and inject liquids into the system. But it can be eventually modified as a gas phase instrument. And yes, it would be suitable for field measurement once it's online. It just looked like a big T kind of thing. Mm-hmm.
Anybody else? So I'll try one fairly general question. How dynamic do you think the condensed phase is? How chemically active is it? You know, do you have a sense what would be the fate of a organic nitrate potentially in an aerosol? And any idea of how much we know about that chemistry, what's left to be known of the condensed phase chemistry?
I think there's a lot to need to be learned. Just like the organic nitrate, when I try different standards, even if I try to dissolve them in different solvent, like polar solvent or non-polar solvent, they would somehow decompose. And especially you add acid into it, they will decompose like immediately. So there's a lot to learn on that part. So, but it has to start from being able to see them in the particle phase first, I think.
Absolutely, yeah.
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 And I think also studying the transformation of reactive oxygen or nitrogen, especially in the biosphere interface, represent a very new revenue and new direction, because that will impose the health impact onto the biosurface.
Got a couple coming here. Mary first.
So just to follow along that question, what's your feeling in terms of things happening in the aerosol water versus happening in clouds? Do you think one dominates over another, or?
You mean cloud processing?
Cloud processing, yeah.
I think for certain species, cloud processing is really important, and we have actually an expert right there on the glyoxal cloud processing. That really depends on how water soluble the species you are looking at.
Well, but what about like in terms of the organic nitrate or organic peroxides?
Well, there have been studies on the hydrolysis of organic nitrates, but I think those sort of studies are not many, I guess. So I can't put a lot of comments on how important it is or not, because we don't have a lot of data basis. Yeah.
So I had a question about your future work. The idea that the epidemiological studies that don't distinguish between the different particles making up the 2.5 and that some might be more toxic than the others. How do you propose to answer that question?
I think the approach I would like to pursue is to eventually represent the different chemical classes in the regional model and use the regional model to predict the regional model predictions as the exposure assignment rather than concentration itself.
But that type of study relies upon a pre-existing epidemiological study that's used to map exposure to basically toxicity or injury. So you would need to have an epidemiological study that would distinguish between the different species in the exposure prior to applying it to the model. That's right.
I think what I understand is a disease model is pretty much built upon the data you have. You have the hospital visit and death data, and you just run regression.
And a bulk exposure.
Yeah.
But in order to make that work, you would have to distinguish between the species and the bulk exposure.
Yes. So the exposure assignment comes from how you can actually predict the exposure.
Right. So how are you thinking to do that? I mean, that's the hard part.
Yeah. I think we need to constrain the model performance by providing more chemical information into it. Because frankly, it has been shown that sulfate might not be harmful. It's really the organic content is harmful, but organic compose like 1,000 different species, and it is the toxic species really plays a role. So we just need to classify them, I think.
Rainer.
Thank you for a nice presentation. You have kind of stressed the anthropogenics, probably because you looked at them in the chamber, but the field evidence is that the carbon correlates with anthropogenic tracers, yes, but the carbon is actually modern in nature. So that, how can you unravel that in the context of a pure volatility-driven parameter space, as I kind of gathered you see models expand? So the conundrum of modern carbon being enhanced by anthropogenic tracers.
Oh, okay.
Can you comment on that?
Well, I think the issue could go to how to represent the gas particle partitioning for a large carbon mass that can be part of not liquid. Well, the Asia system, I think it's just we have a lot of sources for the aerosols we haven't figured out, right?
I just didn't pose my question very, very specifically. Is there an enhancement of anthropogenic factors on the biogenic carbon? So in absence of the anthropogenics, would you think the biogenics basically form the same amount of SOA as in the presence of anthropogenic? Is that anthropogenic, biogenic interactions? Because I kind of heard you kind of decouple them into components and then they would kind of add linearly, or is there feedback effects?
Okay.
What's your opinion on that?
Okay. To continue your last question, I think the enhancement due to anthropogenic emissions has been studied a lot on the sulfate itself. I mean, especially for China, as I know, the presence of a lot of sulfate and the acidity of aerosols really increase all the organics to accumulate. And for your second question, the anthropogenic emissions on the biogenic hydrocarbon chemistry. I think it has been a hot, interesting area for a while. Just like when we first found those crazy highly oxidized molecules in the lab. We use a very simple surrogate, just alpha-pinene and ozone. We never consider NOx. But it turns out there have been a few measurements showing these highly oxidized molecules with nitrogen in it. So there's definitely an impact. To what extent the impact will be, I think that requires more study.
All right. Well, let's thank Xuan again, and thank you for all coming.